Welcome back. Today we are exploring LLMs beyond text, how language model architectures and techniques are being applied to robotics, biology, science, and other domains.
The transformer architecture isn't just for language. It's becoming a universal tool for sequence modeling across many fields.
Let's start with robotics. How are LLMs being used with robots?
One approach uses LLMs as high level planners. A robot receives a natural language instruction like make me a sandwich. The LLM breaks this down into steps: get bread, get ingredients, assemble, etc.
These high level steps are translated into robot actions by lower level controllers.
The LLM provides the reasoning and planning, leveraging its word knowledge.
Another approach is vision language action models. These multimodal models take images from the robot's cameras and language instructions as input.
They output actions, motor commands that the robot should execute. Models like RT2 from Google and PahalME combine vision, language, and robotics.
The transformer architecture processes visual tokens, text tokens, and action tokens together.
This enables robots to understand and execute complex, language specified tasks.
Training these models requires robot interaction data observations paired with actions. Large scale robot learning data sets are being collected to enable this. Let's talk about AI for science, starting with biology.
Proteins are sequences of amino acids, similar to how text is sequences of words.
Language model architectures can be applied to protein sequences.
Models like ESM from Meta are trained on millions of protein sequences.
They learn representations that capture protein structure and function.
These representations can predict protein properties, design new proteins, or understand mutations.
AlphaFold from DeepMind uses transformer like architectures for protein structure prediction.
It achieved breakthrough accuracy in predicting 3D structures from amino acid sequences.
DNA and RNA can also be modeled as sequences.
Models trained on genomic sequences can predict gene expression, identify regulatory elements, or design genetic constructs.
This has applications in medicine, agriculture, and biotechnology.
Let's discuss chemistry and drug discovery.
Molecules can be represented as sequences, smile strings encode molecular structures.
Language models can generate novel molecules, predict molecular properties, or optimize drug candidates.
This accelerates drug discovery by exploring chemical space more efficiently.
Models can also process scientific literature to extract knowledge.
LLMs trained on chemistry papers can suggest synthesis routes or identify promising compounds.
Now let's talk about mathematics and theorem proving.
Mathematics is highly structured and formal, making it amenable to language model approaches.
Models can be trained on mathematical proofs, problem solution pairs, or formal theorem statements.
They can generate proofs, solve problems, or suggest lemmas.
Projects like lean theorem proving with LLMs show promise.
The models can assist mathematicians in discovering and proving theorems.
Similarly, for code, which we've mentioned before,
Models like Codex, CodeLLM, and StarCoder generate code from natural language.
they understand programming languages as sequences, similar to natural language.
This enables not just code generation but also debugging, code translation, and documentation.
Let's discuss scientific discovery more broadly.
LLMs can process vast scientific literature, identifying patterns and connections,
They might suggest novel hypotheses by combining knowledge from different fields.
or assist in literature review, finding relevant papers for researchers.
There's also the concept of AI scientists, systems that can design and execute experiments.
These would combine LLMs for reasoning with tools for experimentation.
We're still early in this, but progress is being made.
Now let's talk about climate and earth sciences.
Weather forecasting and climate modeling involve complex sequential data.
Transformer models are being applied to meteorological data.
Google's GraphCast uses transformers for weather prediction, outperforming traditional physics based models in some metrics.
These models can process atmospheric data and predict future states.
They complement traditional approaches, offering faster or more accurate forecasts.
Let's discuss multimodal scientific models.
Science often involves multiple modalities: text, images, data tables, graphs, equations.
Multimodal models can integrate these different types of information.
For example, processing a scientific paper with text, figures, and tables together.
Or combining satellite imagery with textual reports for environmental monitoring.
The transformer's flexibility makes it well suited for this integration.
What about reasoning and hypothesis generation?
Scientific reasoning requires chaining together evidence, making inferences, and handling uncertainty.
LLMs are improving at multi step reasoning, which is crucial for scientific tasks.
Techniques like chain of thought prompting help models show their reasoning.
But scientific reasoning requires rigor and accuracy that general LLMs don't always achieve.
Specialized training on scientific data and tasks helps.
There's also interest in combining LLMs with symbolic reasoning systems.
The LLM handles natural language understanding, while symbolic systems handle formal logic.
This hybrid approach leverages the strengths of both.
Let's talk about data modalities beyond text.
Time series data, stock prices, sensor readings, patient vitals can be modeled as sequences.
Transformers are increasingly used for time series forecasting.
Audio waveforms or spectrograms are sequences that transformers can process.
We mentioned speech earlier, but there's also music generation, audio classification, and sound synthesis.
Video combines spatial and temporal dimensions.
Video transformers process sequences of image frames to understand actions, events, and narratives.
Graphs and networks, social networks, molecular graphs, knowledge graphs can also be processed.
Graph transformers adapt the attention mechanism to graph structures.
Let's discuss the common principles across these applications.
First, treating data as sequences or sets that can be processed with attention.
Second, learning representations from large amounts of data.
Third, transfer learning, pre training on broad data, fine tuning on specific tasks.
And fourth, scaling laws. Bigger models and more data tend to improve performance.
These principles from language models generalize surprisingly well.
What are the limitations when applying LLMs to these domains?
Domain specific data may be scarce compared to language data.
The structure and constraints of the domain might not align with how LLMs work.
For example, scientific models need to respect physical laws, which LLMs don't inherently know.
Evaluation is often harder. In science, correctness matters more than plausibility.
And integration with domain specific tools and workflows can be challenging.
Despite this, progress is rapid.
Let's talk about the future of LLMs in science and beyond.
We might see AI assistants for every scientific field, helping researchers with routine tasks.
Accelerated discovery through AI suggested hypotheses and experimental designs.
More capable multimodal models that integrate diverse data types.
And potentially AI systems that make independent contributions to scientific knowledge.
There are also ethical considerations specific to these applications.
In healthcare and biology, errors can have serious consequences.
AI designed drugs or proteins need rigorous testing before use.
In climate science, predictions might influence policy decisions.
Ensuring accuracy, transparency, and appropriate oversight is crucial.
So, to recap, transformer architectures and LLM techniques are being applied beyond text to robotics, proteins and biology, chemistry, and drug discovery. mathematics and theorem proving, climate science, and many other domains. Multimodal integration and reasoning are key challenges. Domain specific data and constraints require adaptation, and these applications have enormous potential to accelerate scientific discovery and practical applications.
Next episode is our finale, final reflections and the roadmap ahead for LLMs.
Thanks for listening.
Until next time, keep learning and stay curious about AI.